so our warm-up that we did was this here. There are a couple of different ways you can go about this. I'll show you both ways. But raise your hand if you used congruent triangles to help you out. Wonderful. What'd you say? You were going to. Alright. So let's go ahead and take a look at how we can go about this using congruent triangles. So we're given that RS is congruent to UT. And we're trying to show that RT, this whole thing, that this whole thing is congruent to this whole thing. Alright. So we have our given RS is congruent to RT. That's given to us. Alright, so in trying to show those triangles are congruent, what did we use? What's something that we used?
You can say RVS and UVT are congruent.
RVS and UVT, I like that. So you're saying these are congruent? And how do I know that angle RVS is congruent to angle UVT?
It means that.
Right, so vertical angles theory. Alright. Great, so we've got a set of angles. What else can we say?
Angle R and angle U are congruent because inscribed angles that share the same arc.
Very good. So angle R is congruent to angle U. Okay. Angle R and angle U are congruent. If we look, they intercept that same arc. So inscribed angles that intercept the same arc are congruent. Very good. So inscribed angles that intercept the same arc are congruent. Now, just real quick, let's talk about notation here. I am able to call this angle R. I don't have to use the 3 letters. It's great if you did, but I don't have to use 3 letters because this is the only angle happening here. An angle is made up of rays, which means this is not an angle. I cannot have part of the circle in a segment and that be an angle. That is not an angle. So there's only one angle happening there, and that's angle R. If you use 3 letters, that's great, but it was not necessary to do so. Same thing with U. This is the only set of rays that are creating an angle. This guy and this guy, those are not angles. Okay, so now I have 2 sets of angles. I need still something else to show the congruent triangles. What can we say?
So angle S and angle T are congruent to the same thing?
Yeah, so we could say angle S and angle T are congruent by the same set here, but that still only gets me 3 angles. I still need something else for them to be congruent. Lucy?
RS and T are congruent because they're not circles, they're arcs.
Good, so segment RS is congruent to segment UT. And again, we have congruent arcs have congruent chords, vice versa. So I'm just going to say congruent arcs have congruent chords. Okay, so again, you could have used angle S and T like Sam said, or angle R and U. You could have used both of them actually and ignored the vertical angles here. All right, so we've got those are congruent. So now can I say my triangles are congruent? Yes, on hit.
For RS is congruent to UT, can you also say like converse of like 2 chords that are congruent in their arcs?
Yeah. Yep, that's perfect. Fine. Yeah, you can say converse of 2 chords that are congruent. Yeah, that's fine. All right. So now that I can state triangle RVS is congruent to triangle UVT. What's my reasoning for that?
AAS.
angle, angle, side. Now, again, if you used angles S and T like Sam said, you can have angle, angle, side. If you did not use vertical angles, but you used that S and T are the same, what would your reasoning be? Angle, side, angle. Okay, so you do have a couple of options. All right. Raise your hand if you got to this point of showing those triangles were congruent. Awesome. So now, we need those full segments to be congruent. How can I do that? What do I need to do? Where did that voice come from? What did you say? Segment addition postulate. So RT is made up of RB and VT. I cannot just jump straight to my proof statement because these are not coming from those triangles, but the pieces come from the triangles. Okay, so I need to do segment addition postulate, but what allows me, what do I do with that segment addition postulate? What am I going to do with it? Yeah, we're going to substitute in some pieces. So you can do segment addition postulate next, or you can do the CP-CTC next. It doesn't matter. Let's go do the segment addition postulate. So we're going to need it for RT. Is congruent to RB plus VT. And I need to do it for the other one as well. US is congruent to UB plus VX. Alright, so it's segment addition postulate. And we want to get these to match perfectly so that I can say that they are congruent. So I'm going to need to replace those pieces. So we need to state that the pieces are congruent. So we've got RB. What is RB congruent to? UB, good. And
SB is congruent to T.
Thank you. SB is congruent to T. How did I know that those pieces were congruent? Good, CPCTC. Okay, so again, you can switch those steps. It does not matter which one you do first. Alright. We're almost there. Now again, I need these to match up perfectly. So you get to pick which one you want to substitute. I'm going to go ahead and change RT. So instead of RV, I'm going to use UV. Instead of VT, I'm going to use VS. Now I can see that these have the same components. Okay, what's my reasoning for step 8? Substitution. And now can I make my final statement? See if I can squeeze it in there. For the next one, you can actually go either way. Yep. Alright, was it RT came first? RT is congruent to US. And what's my reasoning for that? Substitution. You could also say transitive since we are replacing the entire thing. So substitution or transitive. Nine steps. Alright, so again, the big ideas were congruent triangles and then that segment addition postulate. Raise your hand if you successfully did the whole proof. Very good, very good. Alright, questions on that? Alright, now I'm going to show you another way that we could have done it in about 6 steps. So I'm going to pull up the fresh page for it, but do we have any questions on this before I do it again? Okay. Start off with the same given. Now you can write this down or you can just watch, whichever you feel like. Alright, so we are given that RS is congruent to UT. And if we look at it, you guys said that congruent chords have congruent arcs, right? And vice versa. Do you agree with that? So the proof statement is this chord RT. Notice the arc that goes with it. And then the proof statement says US. Notice the arc that goes with that. Do those arcs look congruent to you? We know that the red pieces are the same. Don't they just share that same piece there? Yeah, so for the whole segment addition postulate, angle addition postulate, we can also use that with arcs. So I'm going to say that RT, so arc RT, is made up of RS and ST. Do you guys agree with that? Yeah. Okay. And likewise, I'm going to go ahead and state what US is made up of. Well, 50 states, but for this problem.
Good one.
Thank you. So UT and ST. Do we agree with those two statements there? Now this is arcs that we're doing with, so it's just your arc addition postulate, just like segment addition and angle addition. Arc addition postulate. Okay, and once again, if I can get these to match up, then I can say my arcs are congruent, and thus those chords are congruent. How can I get those to match up perfectly?
You already stated that RS and UT are the same, so use substitution.
That sounds wonderful, Woody. RS and UT are the same, so let's substitute that into one of our segments. I'm just going to do the first one. So RT instead of RS, I'm going to use UT. And ST. And that's just substitution. Alright? Now, they match perfectly. So I can say arc RT is congruent to arc US. These guys are congruent. What would be my reasoning for step 4? Substitution or transitive. Is that the pizza delivery guy bringing my Alright, and now that I have that the arcs are the same, the chords are the same. So now I can say RT, because that is the chord that's made up of arc, T, is going to be congruent to US, because that is the chord that's made up of the arc. So once again, congruent arcs have congruent chords. That was 5 steps, not even 6. Look at that.
I was thinking about it, so
Yes, yeah, right.
yeah.
Alright, so I guess technically step 2 you could have just questions on this? Again, either way is fine. You'll notice that triangles are a common key thing to use in our proofs. I think all the proofs we've done so far have dealt with triangles. But here's another way to do it. So that arc addition postulate is another tool. Also, keep in mind that how many degrees are there for all of our arcs? 360. So just keep that in mind. Sometimes that's helpful, sometimes not. Questions with that? Okay. Go ahead and get out your notes pack from like day 1, day 2, the staple thing.
You know, I plan to do it too. You know, I mean, I'll set ahead. That.
All right, I believe we are on the very back side. It's like the top right and then the bottom ones. So on the back side of those notes, written up here, this is lesson 3, it's day 4. Go to the back side, keep flipping, keep flipping. Boom.
Dude, I was facing this the whole time. Wait, no. What? I don't even have it.
I'll let it go this time.
Alright, did we all find our spot in the notes?
Yes.
Okay. So today we're learning our final theorems for circles, and what we're learning today deals with segment lengths. So we're going to be looking at segments inside the circle and segments outside the circle. You all right over there, Williams? Do you need anything?
No, I'm fine.
Okay. Alright. So our first theorem here is talking about when we have 2 chords inside the circle. Okay, so we can see here I have chord CD and chord AB, and they intersect inside the circle. So we've talked about how to find the angles that are made up from those chords. Today we're going to be talking about how to find those segment measures. So taking a look at this, we have EA, so this piece, times EB, this piece, equals EC, piece, times AB. So I like to say piece times piece equals piece times piece. So the pieces that the chords are broken up into, multiply those together, and that's how you get your formula for it. So for this example here, again, I have chords intersecting inside my circle. We can see they intersect right there. So my step is going to be piece times piece, so x times 18, equals piece times piece, 12 times 9. Not too bad. And then we solve. Questions on the setup, though? Okay, I'm going to make this look more like an 18. Now, you could go through and actually multiply 12 times 9, but that's going to give you a big number, and then you have to try to divide that by 18. Work smarter, not harder. Divide both sides by 18, and then just reduce. I can reduce 9 and 18, right? That brings me 1 and 2, right?
And then 2 and 12.
Oh, and then we can reduce 2 and 12. 6 to 1. So what's our answer for x?
6.
Look at how nice and easy that was. Now you can reduce it differently. You could say 12 and 18 both divide by 6, then go from there. But reducing your factors makes it easier to find your answer rather than deal with the big numbers. If I were to actually multiply everything out, 12 times 9,
108.
108, and then divide that by 18, that's going to be kind of hard to do. Again, I would probably go, okay, I can probably cut these each in half, so it'd be 9 and 54, and then 54 divided by 9 is 6. So you can multiply it together, but it's probably easier, especially when we're dealing with larger numbers, just like we've done throughout the year. Reduce your factors with it. Okay, questions on that one? Yes, please.
You know if those chords are congruent.
They don't have to be congruent. We don't know. Just any 2 chords inside a circle that intersect. You do piece times piece times piece times piece.
But how are they even equals?
So it's essentially they're proportional. Because it's not saying that AE plus EB equals those. We're saying that the pieces multiply. So essentially they're proportional. The pieces are proportional. Other questions with this? Alright. So let's take a look at those following things. So now we have segments that are going outside the circle. So we've got secants and we've got tangents. It's actually the same formula, if you would, for both situations, but you'll see how with the tangent's a little more simplified. Alright. So again, I have segments that are going outside my circle here. I've got two secants. Doesn't really matter if they're secants, but. So our formula is going to be outside. And I'd recommend if you have colors to use it, or you can just call it like outside sub 1 if you want. Outside times the whole equals my outside times the whole piece once again. Or outside times the entire. Outside times whole equals outside times whole. Okay, so inside it was piece times piece. Here it's outside times the entire segment length equals outside times the entire segment length. Let's take a look at a setup for this. And I forgot to write this one down. Hold on. So I'm just gonna make one up here. And I think give me a moment. Alright, so we have 2x 4 and 6. Okay, so throwing in some actual numbers here, let's go ahead and solve for x. Now before you begin to solve, I highly recommend that you go ahead and label what the entire piece is for both of these guys here. What is this entire length going to be? 2 plus x. We're adding those pieces together. So 2 plus x or x plus 2. And then what is going to be? And what's going to be the whole thing here? Okay, that. Right. Now, I recommend you do that because the common mistake students make is that they just multiply the pieces together. So, I recommend that before you begin, stay with that whole thing is so you've prompted yourself, hey, I'm not supposed to just do the pieces. Okay, so now as we go through and set it up, it's outside times the whole equals my outside times the whole. Okay, so outside times whole equals outside times whole. Go ahead and solve for x here. See what you think.
I got 18. Isn't it called black?
Alright, what did we get for our answer? Anyone else get 18? Awesome. Alright, questions on that one? Okay. Now let's take a look at this problem over here. It's again the same setup. but it simplifies down kind of nice. So we still do outside times whole equals outside times whole. For this segment, for this tangent, what is the outside piece? The whole tangent, right? So the outside piece is this whole tangent. Are you guys okay if I call it tangent? Okay. So it's outside times whole. What's the whole piece? The same thing. The whole segment is just tangent. So we would have tangent times tangent. What is tangent times tangent? How else could I rewrite it?
Tangent squared.
Tangent squared. So I'm just going to rewrite that as tangent.
You know we're squaring words?
Well, it's because I didn't put a variable for it. Alright, so when we have that tangent, outside times whole is just itself squared. Alright, and then once again, we have outside times the whole. Alright, so similar setup, same idea, but when we have the tangent, that gets squared. Right, Paige and Amani? Questions on our setup here? Okay. Yeah, and then you'd be talking during class. That wouldn't be good either. All right. So let's go ahead and take a look at an example problem for this. We'll make it up. Hopefully it works out nicely. Let's call this guy X. Teresa, give me a number. 4. 4 it is. William, give me a number.
0.
13.
Why? Oh my god.
It's not bad. It's a good one. It's a nice prime number.
It's a bad number. Come on, man.
No, I think so. Harder.
All right. So setting it up, outside times whole, it's going to be x times x, or x squared. Outside, and what am I multiplying by?
17.
4.
So,
Wait,
The
what?
whole thing.
Oh,
Remember the whole thing? 17. Whole thing, we have this one. Now, you can multiply 4 and 17 together, but we're just going to simply square root it.
oh.
Isn't it already broken down into a perfect square and a prime? Yeah. See, you guys were upset with William over here, but he made your life easier by making it a prime number.
I'm thinking a step ahead.
Oh, wait.
Give me another.
Oh, wait.
don't take
So, again, you can multiply those together, but you're going to have to break them down anyway. So, let's leave it broken down. So, would you guys agree with 2 root 17?
Yeah.
Now, it's technically plus or minus, but can I have the negative here? No. No. So, we want just the positive. All right. Questions on that one? Okay. We're going to do some more practice with this. That is countless. I don't think it's one thing. I take it back. We're going to pass this out first. This is not the practical. This is my gift to you.
Thank you.
Oh!
If you
It is
hurry.
now.
Well, if you hurry, then maybe I will. You can be with me. Don't forget to remember.
Is there anyone that did not get this beautiful packet? Quiet down over there, Peanut Gallery. Is there anyone that did not get this? Alright, so what this is, we have now learned every single theorem with circles. And so this is a beautiful document, putting them all together in one place. Let me see if I can pull it up here for you. It's just for start, but it's all nice and neat with examples.
Yeah, mine's really messy.
Alright, give me just a moment. I'll pull it up here so you guys can see what we're doing.
Here we go. Dad, with the pencil.
You ready?
I'm the one who always gets in trouble. You're having no trouble at all.
Because Julius Caesar and Augustus Caesar wanted their own months and wanted them to have more days than the rest, so they took the 2 from February. That's why it's 31 and 31. Isn't that interesting?
That's a 10 on
That's for September.
Otherwise, it would have continued to alternate 30, 31, 31, 30, 31, 30, 31, 30.
We've been new.
We won.
We knew that.
So it was 30.
Lucy, what was your favorite category?
Oh, that one.
Yeah, you got.
I don't either.
There's not exactly 365 days in a year.
You'll count.
Isn't it like one of those?
It's plus a little bit, so every 4 years they throw in an extra day to complete the cycle around.
Wait, what?
What about the last one?
Right here. Again, this is a nice, comprehensive diagrams and pictures and all the theorems and whatnot together. So use this to help you study. Here's even the formulas for our angles and our segment measures that we just looked at. And the equation of the circles even snuck down on there. So this is just kind of comprehensive list of all of our theorems. Use this as you're studying and preparing for stuff, or if you forget what something is, you can look back in here. Okay, that is side note. Now let's take a look at practice problems. Yes? Nope. Because the numbers are specific to the textbook. So if I were to give that to a geometry class in Ohio, they'd be like, yeah, that's not the same as our numbers. So that's why we have to call the theorems, if they have a name, by name, or what the theorem says.
The numbers will be harder to hold.
It's easier to remember just what the theorem says. You cannot call it by its number.
Yeah, let's go. I didn't realize that until I got
Then whatever teacher you have there, then I'll follow you to Ohio.
H what?
Alright, so I want you to take a look at number 11 on this classwork that I just passed out. Number 11. Now we're going to work on it right now. Alright, so let's take a look at number 11, 12, and 13. You'll notice at the top of our classwork here, this is dealing with angles. So we've done quite a bit with that. Let's go ahead and take a look at the things we learned today. So for number 11, I just want to make sure that we get the setup for each of these, and I'll have you guys solve them. For number 11, we have outside times, what is my whole? 11 equals outside times whole, which is just y squared. Notice we are looking for the segment lengths. Our variable or our measures always go from point to point, so y is just talking about this here. We cannot measure a row. Okay, so don't think that you have to go beyond. Alright. Questions on the setup for number 11 here? Alright, now let's take a look at number 12. So we have chords inside our circle and they throw in the radius there. X is talking about this piece. Right? So they want us to find X. We have chords inside the circle. So normally, I would set it up as piece times piece equals piece times this whole thing here. We've got to figure out what that is, though.
24.
Is it 24?
24 minus x.
24 minus x. Sam, how did you know it's 24 minus x?
It's the diameter minus x.
Very good. So this whole thing is my diameter. X has already been accounted for here. How did we know our diameter was 24?
Use 12.
Right, my radius was 12, so my diameter is 24. So the whole thing's 24, but then x has already been taken. So this piece here is 24 minus x. 24 minus x. Okay, questions on that side? Okay. Number 13. Oh, this one's outside. So again, segments are going outside, so we have outside times the whole. What is my whole piece going to be? Good. Z plus 12 or 12 plus Z, however you want to write it. Equals outside, which is 4, times the whole thing, 12. Okay. So I want you to take the next few minutes, work with your shoulder partner, solve 11, 12, and 13. But I want to make sure we're good on setup. And do we have any questions on the setup before we? Okay. So go ahead and work on solving those. If you finish before we come back together, then just start working on the front side.
Why is it?
All right. So number 11 wasn't too bad. Number 12, what did we have to do? Factor. Number 13, what do we have to do here? Quadratic formula. We can't factor it, and we still need to solve it. We're trying to get x equal. Now, if we were just factoring, we would write prime, but we're solving. We're getting x equals, well, z equals. So we have to use quadratic formula for this, right, Amani? Put that away.
Are you kidding? C is 48.
Now again, 11 shouldn't have been too bad. What did we get for our answer for y? Good, square 22. Technically we have plus or minus, but we take only the positive. Alright, so number 12, when we multiplied everything out, we should have gotten x squared minus 24x plus 8.
I need something.
Why did I get that?
And I don't think that's.
I got it.
Do we need explanation to get to this point?
No.
No.
We good? Okay.
I'm almost there. One more time.
Anyways.
So you get positive 24, negative x. So when you add your x over, subtract your 24, your 80 is still positive. You could have subtracted the 80 over, and then you would have had to factor out a negative. I don't like that. Alright, so we need what multiplies to 80, adds negative 24. William, focus. Alright, when you see 80, what are your first thoughts of factors? 20 and 4. Which conveniently works out, but let's say we didn't get there. Let's say we did 10 and 8. Now, as we get to deal with large and larger numbers, remember, work smarter, not harder. So break this down into the factors you know it can be. So now I can say, hey, if I group the 2's together, then that's 4 and 20. Or you can take, actually, that's about all you can do. I mean, we could do the 2 times 2 times 4. And go 16 and 5. But you can use that, break it down to its factors to help you out if you don't think of those factors right away. Alright, but we said it's 4 and 20. What needs to be negative? Both. Alright, so we should have got it factored into x minus 4. X minus 20. So we get x equals 4 x equals 20. Raise your hand if you got to this point. Okay. Alright, so let's talk about this. Can we take both?
No. It's not logical.
I have
Can't take
Four. It has to be that long. Because if this is 12, and this is 12, and this is a piece of 12, then it can't be.
okay, so say that again.
Okay. If this piece is 12, yeah, that one, and then the other full piece is 12, then a part of that whole 12 can't be bigger than 12, so it can't be 20.
Okay.
Whoa.
So what Lucy's saying here is, I know that this is a radius, and my radius is what? 12. Can I have part of that radius be 20?
No.
No, because
What's
the-
the other part?
right, but we can't have a negative distance, right? Okay, so are you guys okay if I do this? Does that make sense why we are throwing out the 20? Okay. Alright, now with 13, when we multiply this all out, we should have gotten z squared plus 12z minus 48 equals 0. Are we good with that? Did I have my signs right? Okay. Now, if I look at my factors for negative 48, what's the first thing you think of for 48?
12 and 4.
12 and 4? I was going 6 and 8, but that's okay. We'll do 12 and 4. Alright, so we also have 1 and 48, 2 and 24, 3. Does 3 go into 48?
I don't know. Oh, yeah. Because 12 is...
I'm so glad you said that, Lucy. We know 3 goes into because 12 is a factor. Since 3 is a factor of 12, then 3 must be a factor of 48. So 3 goes into it, 3 and what? 16. Alright, we've got our 4 and 12. Does 5 go into it? Nope. 6 go into it? We've now listed all of our factors. In order for our 12 to be positive, we would need the smaller ones to be negative. But do any of these add up to be 12? No. So this is not factorable, which means we have to use quadratic formula. And when you use quadratic formula, you end up getting an answer that I'm going to tell you momentarily.
Where?
Okay, so we get negative 12 plus or minus root 336 all over 2. Now we can simplify this.
Yeah, I simplified it.
Are we good with this? Questions on this? Okay. Now when we simplify this, we get negative 12 plus or minus 336 is definitely divisible by 2 because it's an even. And we keep breaking it down and we get 4 root 21 over 2. Questions so far? Now remember, we always simplify as much as we can. And we can simplify because each of these 3 pieces have a common factor. Which means
Plus 2 root
negative 6 plus or minus 2 root 21. Questions on that? Okay, but negative 6 minus 2 is definitely a negative number, so can I have that be my answer for Z?
No.
Nope. Now 2 root 21 is going to be larger than that negative 6, so I want for my final answer. Oh, okay. We'll just do that. I want for my final answer negative 6, and I'm taking only the positive 2 root 21. Raise your hand if you got all the way down to the end. Very good. Very good. Alright, questions on those 3? You got negative 1. I think you might have subtracted instead of adding. Alright, now flip your paper over. And let's take a look at numbers 17, 18, and 19. Reading the directions, what are we looking for here?
The arc.
The diameter. The diameter.
Oh,
17, 18. So we're looking for the diameter here. Let's take a look at 17. This one's interesting.
you do the
Pythagoras.
yeah, that one.
I said it wrong. I'm sorry. I'm sorry.
Pythagoras is his name.
It doesn't go all the way down.
Pythagoras.
The Pythagorean theorem. Good. So we have this chord and this diameter. They tell us that they are what?
It's alright.
It's perpendicular. And so that means this is also perpendicular. So we have conveniently a right triangle. Now, Ankit, what is that thing called again?
Pythagorean theorem.
Very good. Pythagorean theorem. Now, let's go ahead and call this whole thing here. What do you guys want to call it? X. Great. Go ahead and solve for x using Pythagorean theorem. I want everyone to solve for x right now.
Happens multiple times a day.
Wait.
That's not true.
So what do we get for x?
It's 4.
Anyone else get 8?
I have 2 root 3.
Alright.
Wait,
So, real quick, what is 10 squared? 6 squared?
36.
100 minus 36.
64.
I messed up.
Alright, so now I have that this piece here is 8. Okay. Do I have segments outside or inside? They're all inside. So we know we can do piece times piece equals piece times piece.
Oh,
Right?
For the other part.
Now, we don't know this piece. Let's just call that y. So would you agree that for my diameter here, it's 8 times y equals, I have this piece is 6, but how much is this guy here?
6.
Well, how did we know that that was also 6?
Theorem says.
So we have the theorem that says diameter or radius that's perpendicular to a chord cuts that chord in half. What else does it cut?
The arcs.
Minor arcs and major arcs. Good. Okay. So there's our setup for 17. Let's take a look at our setup for 18. So our segments are going outside. So we want outside times whole.
Change.
Can we go ahead and call our diameter just d here? Are you guys okay with that?
Yes.
So what's my whole segment going to be?
12 plus D.
12 plus d or d plus 1. Alright.
Diameter.
So outside times whole equals outside times whole, so 24 squared. Questions on our setup for 18?
I have a question. Yeah, can you tell me what the diameter of 17 is? Because I want to see if I'm right.
What did you get?
You know, we have different answers, so I want
Oh,
you to
wait,
say it out.
We'll look at just a second. Alright, are we good with the setup for 18?
This time with a little.
Alright, let's look at our setup for number 19. Alright, chords inside or out? Inside. I guess the word chord gives that away. So we know it's piece times piece. So 3 times this guy. What do you guys want to call this?
A.
I like that on kit with something different. Let's go with egg. Oh yeah, you could have said L for Lucy. Alright, and then
L.
peas times peas. Do I know this guy?
Yeah.
No.
Yes.
It's 4. It's 4. It's 4.
Yeah, perpendicular, so we know that those get cut as well. Okay, so I want you to go ahead and solve. Remember, we are solving for the diameter in the end. So you might have to solve for the variable and then substitute back and find your diameter. So go ahead and solve for your diameter.
We got 4.5. I can't see.
Yes.
That's good.
I got 5. Wait, is Y a fractal?
Very possible.
Ah, that's an easy number.
Yes.
Yes.
It's like
Wait,
576.
18.
Are you gonna be
18 it is. Wait, no.
What's like no, it's not math background stuff.
I got 5.5.
Or you're subtracting 5.01.
Yeah.
It's like remainders. I'm wouldn't have done this entire work.
I don't know
Can you count that seed? I mean, are you using a calculator? So I got x equals 16 here. Are you down? Are you down when you, I think, those are fine. Yeah, but that means I was not EP10 and EP1.
I got it.
Oh, it's still
That's like 9.
Because 3 goes into 10.
So 3 and 30. I would like to write that. But I don't know.
Yeah, when do the other classes?
Alright, what did we get for y over here?
4.5.
4.5.
9 over 2 or 4.5. But is y my diameter?
No.
No. So what did we get for our actual diameter?
12.5.
12.5 or 25 halves.
That was so
Alright, questions on 17? Alright. Lucy, what did we get for our diameter here?
36.
36. What is 24 squared?
5.7.
Good. It's 576. Alright. And then, did anyone happen to finish out this A? Oh, we can do A. What do we get for A?
16.
16 over 3. And then what do I need to do with that to get my diameter?
Add 3.
Add 3. So what is my diameter for this guy?
25.
Good. 25 thirds. Okay. Taking a look at your assignment sheet, what is your homework? Worksheet 5. And what's happening next class?
Okay.
Are you ready?
Did we just say anyone want to dude, they're so cheap. Not cheap. If they are, they're like $3. It's fine. Look at this. I caught it on. I was trying to take my stuff. And it's not for
Wait, where's my phone? Alright, you guys are good to go.
I don't even know.